In this lecture, I shall discuss impulse functions, which are also known as Dirac delta functions, and how to solve differential equations involving those functions. So in some applications, it is necessary to deal with phenomena of impulsive nature, which are actions that have very large magnitude, but happens on a very short period of time. That's impulsive. So large magnitude but acting on a very short period of time. So as an example, in nature, when we push a swing, at a certain time we push a swing and we give a large force, but in a very short amount of time. Similarly, if we use a hammer to hammer a nail, then the same thing happens. Large force, but acting on a very short period of time. So to give a mathematical model, for now, let's use t for the independent variable. Usually we use x for the independent variable. We'll switch to x later on, but for now, t represent time. And suppose we have a constant force. Which means that the force is a constant. It doesn't depend on time. Acting on an object at a certain time, say t equal to c, and we let delta t denote the time period that the force acts on the object. So the action of the force may happen a little bit before the time t equal to c and a little bit after that. So if we sketch the graph of the force, and it looks like this. This is the time interval t, the time t, and then this is for force. Right here we have c. So assuming that the force acts a little bit before c and a little bit after c, so the graph of the force looks something like this. It's 0 at the beginning, and then the constant force, and then 0 again. So recall, say the action of a push on the swing, and this is the time interval delta t. Yeah. Now we define the total impulse of the force. Is the area given by the graph here. The area between the graph and the t-axis So basically, this is the area we're looking at. You see the shaded area, which means that we have the force, whatever amount it is, times delta t, the time period that the force is acting. Here we have a rectangle, and this is the force, the magnitude of the force. Now let us assume that the total impulse is 1. That is, the area of this rectangle is 1, or equivalently, the magnitude, let me just write, magnitude of the force. So it should be the same here, the magnitude of the force times delta t equal to 1. So using this, we see that if t is small, if delta t is small, if the time period when the force acts on the object is small, then because the magnitude of the force is the reciprocal of the time delta t is very large. So this explains the impulsive nature. But when we talk about impulsive nature of force, like pushing a swing or hammering a hammer, we want delta t to be really small. We want delta t to be smaller and smaller, or in other words, we want delta t to goes to 0. So we must sketch some picture like this. It's a t interval again. It's c. It's a force. Let me sketch 2 picture for you. The same setup. But for the first one, we have the interval, to a larger interval. Then say the force, the magnitude of the force like this. To make sure, again, the area is 1. But for the second picture here, say we have a shorter time period, shorter. Then to make sure that the area is still 1, the height should be higher. And so the magnitude of the force should be higher. To make sure, to guarantee that the area is still 1. So when delta t go to 0, the force is very high, it goes to infinity. And using that idea, we have the notion of the impulse function. The impulse function, also known as Dirac delta function. Denoted by the delta sub c here. This is the impulse function at c, is defined to be the so-called weak limit of the above process. as delta t go to 0. Now you haven't seen the notion of weak limit, and we won't discuss much about weak limit. But let me just mention that the weak limit here is different from the usual limit. The reason we want to have weak limit is if you look at the usual limit, then we would have 0 everywhere except at where. So you see when delta t go to 0, the length of the interval here getting smaller, so smaller. And so if we look at the usual limit, the delta function would be 0 everywhere except at c when it has value of infinity, which is not useful. Okay, it's not useful for application. So we need to look at a certain type of limit, weak limit. Now, the important things that we need for our applications to differential equations is the following. Property of the delta function is that the Laplace transform of the delta function, delta c, is e to the minus c times s. This is the formula we need to use. Now it's very similar to the Laplace transform of the unit step function, but don't confuse that the Laplace transform of uc is e to the minus c times s over s. So see the difference here for uc and delta c. More generally, which we will not use it, but sometimes when people talk about the Dirac delta function, they use this property. The integral from minus infinity to infinity of any function g of t and delta c of t dt is just the value of g at c for any continuous function g. So what it means is that when we integrate a function times delta c, then what we get is very simple. It's just the value of the function at c. But we won't need this. We only need the formula for the Laplace transform. So that's for the introduction or the motivation to define the impulse function. But now we will go back to independent variable x, to use x as independent variable. And let's look at an example how to solve differential equation with the delta function. Solve the initial value problem here, y double prime plus 4y equals to delta pi. And here we're using x as the independent variable, so delta pi x. With initial condition, y0 equal to 0 and y prime 0 equal to 1. Because delta pi x is not the usual function, we won't be able to use the method in chapter 3 to solve it. Instead, we need to use Laplace transform. So take the Laplace transform both sides of the ODE, as we have been doing. Then we have Laplace transform of y double prime plus 4 Laplace transform of y equals to Laplace transform of delta pi x. Now let's use a formula. Laplace transform of second derivative is s squared Laplace transform of y minus s times y0 minus y prime is 0. y0 is 0 and y prime is 0 is 1. Recall this is y0, this is y prime 0. And then plus 4 Laplace transform of y. Now on the right hand side we have Laplace transform of the delta function, delta c. We have e to the minus cs, this is pi s. Now we group all the terms with Laplace transform of y together and even factor the Laplace transform of y out. Then we have s squared plus 4 equals to e to the minus pi times s, and this 0 and the negative 1 here becomes plus 1 on this side. Now we solve for Laplace transform of y. We have e to the minus pi s over s squared plus 4 plus 1 over s squared plus 4. So we need to use inverse Laplace transform to solve for y. But before doing that, recall that we don't combine terms with e to the minus cs. Instead, we separate them. So we should write e to the minus pi s here separately times 1 over s squared, and 4 is 2 squared plus 1 over s squared plus 2 squared. This is the Laplace transform of y, and our solution y is the inverse Laplace transform of that. Minus pi s squared plus 2 squared plus inverse Laplace transform of this s squared plus 2 squared. Now the first one is easy to do. We have the inverse Laplace transform of this function s squared plus 2 squared. We use a formula for sine of beta x, where beta is 2 here. So we could rewrite like this, because in the formula for sine of 2x or beta x, we should have beta in the numerator. So it should be 2 here, s squared plus 2 squared. We have a half in front to cancel with the 2 that we have just multiply. And then use a formula. This is just sine of 2x. That is the inverse Laplace transform of s1 over s squared plus 2 squared, like what we have here. Now, for the inverse Laplace transform involving e to the minus pi s, we saw in the previous topic, we need to determine the inverse Laplace transform of this first, right, which we already did anyway. So for the inverse Laplace transform of e to the minus pi s, we need to shift the formula. Let me recall the formula of shifting here. The inverse Laplace transform of e to the minus cs times capital F of s is first we need to look for the inverse Laplace transform of capital F. We get like little f, and we need to shift it to the right, c units. So f of x minus c times uc of x. Here, for this problem, c is pi. And we know that the inverse Laplace transform of this fraction is a half sine of 2x. So we need to shift x here by x minus c, which is pi, and then multiply by u pi of x. Distributing, we would get a half sine of 2x minus 2 pi, and then we multiply u pi x at the end. Recall that sine is a periodic function with period 2 pi. So when we add or subtract 2 pi or a multiple of 2 pi's, we get the same value for sine. So the same sine of 2x times u pi x. Now put everything together. We get our final answer here, that y equals to, let's look back, y is the sum of two inverse Laplace transform, the first one and the second one. The first one above, we have a half sine of 2x times u pi x, and then the second one is plus a half sine of 2x, and this is the solution. Now let us look at another example. Example 2. We want to solve the initial value problem. Y prime minus 4y prime plus 4y equals to delta 1 of x with initial conditions y0 equal to 1 and y prime 0 equal to negative 1. As usual, you see our ODE is non-homogeneous equation. So we take Laplace transform. We will have Laplace transform of second derivative minus 4 Laplace transform of first derivative plus 4 Laplace transform of y equals to Laplace transform of delta 1 of x. Then we use a formula. Laplace transform second derivative is s squared Laplace transform y minus s times y0. y0 is 1 minus y prime was 0, which is negative 1. And we get s squared Laplace transform of y minus s plus 1. On the other hand, Laplace transform of y prime is s times Laplace transform y minus y0, which is 1 here. And also for the right hand side, we have Laplace transform of delta 1 x is just e to the minus 1 times s, which is s here. So we plug into the equation. Normally, I denote by star, which is here. So we have Laplace transform of second derivative, which is s squared Laplace transform of y minus s plus 1 parenthesis minus 4 times Laplace transform of the first derivative s times Laplace transform of y minus 1 plus 4 times Laplace transform of y, and on the right hand side we have e to the minus s. Now it's time to let's collect terms and simplify things. Don't forget to distribute in. We keep on the left side terms with Laplace transform, and we factor that out. We have s squared. When we distribute, we have minus 4s, and lastly we have 4 equal to e to the minus s. This is minus s. We move to the other side, becomes plus s, and then plus 1 and minus 4 distribute with negative 1, we have positive 4. So together we have positive 5. But when we move to the right hand side, it becomes negative 5. You may pause the video and try the algebra yourself. Now let us solve for the Laplace transform of y. Divide both sides, we have this s squared minus 4s plus 4. We don't combine terms with exponential, so e to the minus cs stay by itself, but s minus 5 should be together, okay? Because they don't have e to the minus s. So we write s minus 5 divided by s squared minus 4s plus 4. And our problem now is to determine the inverse Laplace transform. As before, we will split e to the minus s times the fraction 1 over s squared minus 4. We can complete the square. It turns out that we can factor. It turns out we have s minus 2 squared plus inverse Laplace transform of s minus 5 over s minus 2 squared. So we have two pieces to do. Let's do A, which is inverse Laplace transform of e to the minus s 1 over s minus 2 squared. First, we need to look at the inverse Laplace transform of the fraction without exponential e to the minus cs. So we need to look at that first. But this is a familiar formula. It is 1 over s minus alpha squared. The inverse Laplace transform of this is x e to the 2x. Look at the formula with alpha equal to 2 here. So then, when we have e to the minus s in, we need to shift x, and then we multiply by uc, which is u1x here. C is 1. We need to shift by 1 unit to the right. So x replaced by x minus 1. I have an x here. The right here should be x minus 1. And then I have an x here. So it should be x minus 1 as well. which means that let's rewrite e to the 2x minus 2 and then u1x. This is the inverse Laplace transform of the first piece involving exponential e to the minus s. And the second is the inverse Laplace transform of s minus 5 over s minus 2 squared. That's the second piece over here. Let's see B. So we need to do partial fractions. Partial fractions s minus 5 over s minus 2 squared. We begin with a over s minus 2 squared, the highest power, but don't forget the lower one as well. Then by clearing the denominators, and solve for a and b. You may pause the video and try yourself. I'll just write down the value that a is negative 3 and b is 1. And so the inverse Laplace transform of the fraction s minus 5 over s minus 2 squared is the inverse Laplace transform of this minus 3 over s minus 2 squared plus 1 over s minus 2, and we get, don't forget this is the minus sign in front. I'm going to put that. So we get minus 3, and this is x e to the 2x. The other one is e to the 2x. Now put everything together. Put a and b together for the final answer. So rewrite the first piece, first inverse Laplace transform give us this, and the second one is that. So together we have x minus 1 e to the 2x minus 2 times u1x, and then minus 3x e to the 2x plus e to the 2x. And this is the solution to our given initial value problem. This is the end of the lecture.